Now, we've studied matrix vector multiplication and vector matrix multiplication. Now we're going to study matrix matrix multiplication. Suppose A is an R by S matrix and B is an S by T matrix. Then it's legal to multiply A times B. In Mathies, we'd write it as AB. And in our math class, we'll use a star to denote multiplication between matrices, so we'd write it A star B. Now note that A times B is different from B times A. In fact, one of those products might be legal while the other one is illegal. So we're going to see two equivalent definitions of matrix matrix multiplication. One in terms of vector matrix multiplication and one in terms of matrix vector multiplication. We'll start with the definition that uses vector matrix multiplication. Say we're multiplying A and B. For each row label R of the matrix A, row R of AB is the vector matrix product, the row R of A times B. So for example, let's say we're multiplying this matrix by B. Row 1 of the product is row 1 of the first matrix times B. Row 2 of the product is row 2 of this matrix times B. And row 3 of the product is row 3 of this matrix times B. How do we interpret this product? This is a vector matrix product. And we can use either of our definitions, the linear combinations definition or the dot product definition. Either one will do. So we defined a matrix product in terms of some vector matrix products. How do we interpret this vector matrix product? Let's use the linear combinations definition. We write B in terms of its rows. Let's call them B1, B2, and B3. Then the matrix vector product 1, 0, 0 times the matrix B, by the linear combinations definition, just picks out the first row, B1 of B. Similarly, the product of 2, 1, 0 with the matrix B takes 2 times the first row and 1 times the second. So 2B1 plus B2. And the product 0, 0, 1 times the matrix picks out just the third row, B3. So in summary, we get this product. So what is this doing? Multiplying this matrix by this matrix really adds twice the first row to the second row. For that reason, we call this an elementary row addition matrix. Now I'm going to give the matrix vector definition of matrix matrix multiplication. For each column label S of B, column S of the product AB is A times column S of B. So for example, let A be this matrix, and let B be the matrix with columns 4, 3, 2, 1, and 0, minus 1. So here's B. Those are its columns. The product AB is the matrix whose column I is the product of A with column I of B. So A times the first column, 4, 3, is 10 minus 1. A times the second column, 2, 1, is 4 minus 1. And A times the third column, 0 minus 1, is negative 2, negative 1. So the matrix matrix product is the matrix with those outputs as its columns. Now we can combine these definitions, the matrix vector definition of matrix matrix multiplication and the dot product definition of matrix vector multiplication to get what I call the dot product definition of matrix matrix multiplication. Entry RC of the product AB is the dot product of row R of the first matrix with column C of the second matrix. For example, to find the matrix matrix product of these two, we think of this first matrix as rows, we think of the second matrix as columns, and we take all the dot products. And this is the result. Now, matrix-matrix multiplication interacts in a nice and predictable way with transpose. Now, here's the rule. The transpose of A times B is B transpose times A transpose. So, for example, here's a product of two matrices. Call this A and this B. This is the product. Now, if we take the transposes and reverse the order, we get the transpose of this is this. The transpose of this is this. We take the product, and we get this matrix. Now, notice that this matrix is the transpose of this. Now, you might get confused and think the transpose of the product AB is A transpose times B transpose. But that's the wrong order. This is false, and in fact, it might not even make sense. It might be that the row and column labels make that an illegal product. For AB to be a legal product, A's column labels have to match B's row labels. For A transpose B transpose to be legal, A transpose's column labels, that is A's row labels, have to match B transpose's row labels, that is B's column labels. So, for example, this product is legal, but if you transpose them, you get an illegal product. Let's see what happens when we multiply a matrix by another matrix that happens to have a single column. Let's call the column B. Well, by the matrix vector definition of matrix-matrix multiplication, the result is a matrix with a single column, and that column is the matrix vector product A times B. Well, this shows that matrix vector multiplication is in some sense subsumed by matrix-matrix multiplication. If you want to express a matrix vector product, you can always formulate it as a matrix-matrix product where the second matrix is actually one column wide. Now, there's a convention to interpret a vector as one of these one column wide matrix. It's called a column vector. So we would write the vector 1, 2, 3 in this way, as a matrix with one column, namely 1, 2, 3. And then we'd write the matrix vector product A times the vector 1, 2, 3 as A times the column vector, that is the one column matrix with 1, 2, 3. And generally we would write that as A times B without the star in the middle to be consistent with our notation for matrix-matrix product. Now, if we interpret vectors as one column matrices, how are we going to get vector matrix product? We use the transpose. We can turn a column vector into a row vector. So suppose you have the vector B, 1, 2, 3, and you want to take the product of this vector with a matrix. Consider this vector as a row matrix, that is, a matrix with only one row. Then by the vector matrix definition of matrix-matrix multiplication, the product you get is a single row matrix. So we would write this as B transpose times A to be consistent with our convention of interpreting a vector as a column matrix. Since the vector B is a column matrix, the transpose of B is a row vector. That is, a matrix with a single row. Now that we know how to interpret vectors as matrices, either column vectors or row vectors, let's see what it means to multiply them. There are two ways to multiply vectors interpreted as matrices. First, let's take the product of a row vector times a column vector. We'd write that U transpose times V. Here's an example. Let's take this row vector and multiply it by this column vector. Now, the first matrix has one row, and the second matrix has one column. So the product matrix has one entry. It has one row and one column. It's really just a matrix with one number in it. Now, by the dot product definition of matrix-matrix multiplication, that one entry is the dot product of the single row of this first matrix with the single column of the second matrix. So we're really computing a dot product. This is sometimes called the inner product, but we're going to use the inner product in a more specialized way later on. Here's another way to multiply vectors interpreted as matrices. We take a column vector times a row vector. Here's an example. This column vector times this row vector. Using the dot product definition of matrix-matrix multiplication, the entry in the first row and first column of the product is the dot product of the first row of this matrix by the first column of this matrix. Well, that's just the product of this one entry U1 by the one entry V1. Similarly, the ij entry of the product is the product of the ith entry of the first vector by the jth entry of the second vector. This is called an outer product of two vectors.